This is section 3 in Excel, estimating the regression equation. This is the same example that we saw in section 1, 15 sales representatives making calls, different calls, and selling different amount of copiers. And we saw in the first section that if we insert a scatter graph, we get that relationship. Well, this relationship, as if you notice, the sales calls increase, copiers sold increase, indicating that there might be a positive linear relationship between the two variables. We run the regression command by going first to data, then data analysis, then select here regression. This is in alphabetical order, by the way. Click OK. Input the wide range. Here you input the dependent variable, the variable that is being explained, and the X is the variable that explains. Well, in this case, sales calls explain the copiers sold. So copiers sold are, or is, our dependent variable. And the independent variable is the sales calls. I included the labels on the first row. Confidence level is 95% by default. Don't need to check it. And the output range, I'm going to select right here to start at that cell. Click OK. And you get this output. Here you have multiple R. At this point, just notice from a previous section that this is exactly the value that we obtained for R, 0.86 approximately. Now going down here on the output where it says coefficients, the intercept is 1998 and the sales calls is 0.26, the coefficient. So this is our equation. The equation is y hat. Y hat is the estimated value of y, is y with a little hat on top. Y hat is equal to 1998 plus 0.26 times x. So that is our formula, or equation, I'm sorry. This is the regression equation. Now here are values that from chapter 12 you should be familiar with. This is the sum squares of the regression, and this is the sum squares of the residuals, and this is sum squares total. Well, the idea behind this is the following. In a regression line, let's say this is the regression line, the 1998 plus 0.26x, there is, let's say, an actual value right here that has an actual value that we're just going to call it yi. It can be, that is actually a number. And suppose that the average value of y is right here, which we call it y bar. Well, the difference between yi and y bar, same as what we saw in chapter 12, this is called total variation. And the difference between y hat well, let me explain this here. I didn't put it. The value of y right here is y hat. Now, something I have to clarify is all of this is for a specific value of x. We can call that xi, although it's not playing any role right now. So again, we have x on the horizontal and y on the vertical. Y hat is the value of y that is estimated by the line, as you can see right here. This is the actual value of y, and this is the average of y. Just add all the numbers divided by 15 in this case. Okay, if you take y hat and subtract y bar, this is regression variation. This is variation due to the regression. And it's also defined as explained variation. It is explained by the regression. And finally, the difference between these two, this is yi, the actual value of y, minus y hat. And this is error or residual variation. This is also called unexplained variation because it's due to error. The actual value minus the estimated value is a difference that cannot be explained by the model. Only this portion can be explained by the model. So what is, for example, this number, 2326, that's total variation. Total variation is defined as, let me write it here, total variation is defined as the summation of, if you recall right here, this is variation for one single value. So it's the summation of all these differences between each actual value and the mean squared. So take those differences, square them, and then add them up. And you will get 2326. What is 587.11? This is the summation of squares due to the residual, and the residual is the error. So it'll be calculating that variation. So, and that is called actually SSE, the same way it was called before, is the summation of the yi minus y hat squared. So if you do that, you get 587.11. And 1738.89 is the summation of squares of the regression. So that'll be y hat minus y bar. Summation, that is called SSR. SSR is the summation of the y hats minus y bar squared. You can put yi here. All right, so this is a more detailed explanation of where this is coming from, this number, that number, this number. And then the MS of the regression is the same way calculated as in chapter 12. You take the SS divided by degrees of freedom, 1. And this MS, this is the MSE, is the SSE divided by degrees of freedom. Now, the degrees of freedom of the regression equals k minus 1, number of variables minus 1. 2 minus 1 is 1. The degrees of freedom of the residual is n minus k, number sample size minus the number of variables. In this case, sample size is 15. Notice here, observations. 15 minus 2 variables, 13. And the total variation, like we learned also in chapter 12, is always equal to n minus 1. 15 minus 1 in this case is 14. But it is also equal to this plus this. That's the total degrees of freedom.